Hello, and welcome to the final presentation for EL 6825 pattern recognition taught by Dr. Wu. My final project was on audio steganography decoding using feature extraction. In this presentation, I'll give you the motivation behind developing this project, some background information on a few of the terms, the related study of this project, my project design, the results of my code, and my final remarks and conclusions. So to get started, the purpose of this project was to test the students' comprehension of material gained within the pattern recognition class this semester. The main reason is because I have an interest in the field of communications and was interested in the topic of steganography, in hopes to further my education in the subject of confidential communication and secret data storing. Here are a few terms I would like to and had to define for myself to get a better understanding of the project at hand. Steganography first encrypts an actual disguised idea within the files that can only be decoded by the wanted receiver or the sender himself using the features of the original signal. Then you have watermarking, which is second, which is a form of steganography that hides a logo or a symbol of possession within images or audio files. Next is binary masking, which is the technique we'll be encoding the hidden message with. Uh, Basically is an addition of binary array to a sequence. And we have feature extraction, which is the comparison of one signal to the next, and the difference between the two will determine if the signal has been altered in that instance. So now we go to some background information, some on frequency masking, and this is the technique that I will be using for my project. Frequency masking is achieved by finding the magnitude of the signal that will hold the hidden message and altering these magnitudes based on the binary activation of the read-in message. The amplitude is slightly increased or decreased by small factors called the twiddle factor, but the human ear will not be able to hear these changes in amplitudes. Next, we have echo masking, which this technique takes the signal, scales it down, and then reflects it onto the original signal. By doing this, the area that are considered to have an echo will be the areas that was altered by the hidden message. And as you can see, is a demonstration of how echo is thought of, or how echo is processed within the coding environment. And next is phase. Phase masking takes advantage that the human ear cannot detect small shifts in audio sounds, just like the others do. Small shifts in the audio file will indicate that the file has been altered by a hidden signal. This technique is demonstrated, as you can see. To the left is the basically original phase. To the right is the altered phase. If you glance at the right, you can see that it might be similar or in phase with the left phase, and that is the type of phenomena that we're trying to attack here and take advantage of. Then we have a few related works that were related to this project that I was doing. So the first one were is done by Mozad Nasardi, Ronak Karami, Mehdi Harari. Sorry if I messed up the names. But they've shown that there are various techniques for audio steganography, mostly pertaining to some types of modification to the bit stream of the file and the hidden message. My favorite type out of all of them seemed like genetic algorithm, which is based audio steganography. It looks to be the most interesting since artificial intelligence is trying to determine the best place to hide this hidden message. In this case, compared to my research, it provided helpful insight on the various techniques and mainly how and what type of data that will be toiled with in the future or in the past now. The bottom paper, written by Sauce, David, and Sunil, They proposed an algorithm that would take the Fourier transform of the audio and only watermark one-fourth of the bends in the signal. The researchers only encoded a small sequence out of the signal with the secure data to provide more security for the information, meaning they tried to put all of their hidden message within a small portion of the original signal, make it harder to find which signal is actually being distorted or being changed, altered. The difference between their paper and this project is the whole audio file will be encoded with the binary hidden message in this project, and this project also utilizes the binary code to determine which uh, magnitude is scaled, which hopefully will give us some randomization, and we can have security from that. So next, I have my project design, and I'll explain this a little bit step by step. It's very blurry, but the pointed lines are supposed to indicate everything that is actually going on. So from left to right, this is the flow diagram. So first you enter the audio file into the code. So we input the audio file, and if you can look all the way up here by MT, this is the signal that we will be altering the audio file with. So first, since we inputted the audio file, we take the FFT of it, the fast Fourier transform, so we can start messing with the discrete DFT, and you see the mag and the angles are separated as is in the code. Uh, then you get to the checking the message, or this section right here checks the message, the binary message. If it's a 1, if that element is set to a 1, then the magnitude will be scaled, increased or decreased. And if it's set to a 0, then the magnitude will be left alone. Then we get to the combining the mags and the angles, where we get the signal back. We run the inverse FFT, and then we shoot out our new signal. Design of the frequency mask decoder. Um, the first signal and the modified signal will be read in to find both the magnitudes of their DFTs. The magnitudes of both signals are compared using error estimation or feature extraction with the equation that you can see right here. So this is SK minus, this is SK original minus SK altered. Uh, and if the deviation between these are greater than 0.1, then that would be set to a 1, as I mentioned in the previous slide. And if it's not, then it'll be set to a 0. And also I want to show this binary number right here, because this is how actually the message is being encoded into the audio file, into separate 7-bit binary numbers. As far as the results, I conducted a subjective test, which I always ask if the altered sample was the original, which in my subjective test, I had the altered sample and I had the original sample. I played I played the original sample, then the altered sample, and would ask if the altered sample was the original. And for the subject 1, they said it was the original. Subject 2 and 3 said it was not original. So I have 2 out of 3 that were wrong, or 2 out of 3 that were correct. This is good information because it's almost 50%, and we get our best information from subjective tests that are around a medium. And through my objective test, which is the actual coding test, which you'll see a demonstration of later on, I have a song, a clipping of a song called "If I Fall." Uh, Artist is Big Crit, and the encoded message that was read out easily and without a problem was "What a Wonderful Day." The signal to noise ratio between the two signals was 157.78, and you can see the same. I've tried this with two other songs, Float On and Bass, and they both came out to read out the exact same coded message. Computational complexity, the time it took to encode the message was approximately almost 2 seconds. The code ran just that fast, and it's only like 50 lines of code. And then the time it took to decode the message probably was like around 15 to 20 seconds, and it's only 65 lines of code. In conclusion, this is a very effective technique at hiding binary messages within an audio file. It's very fast and can be very simple. Uh, and if you don't know what you're doing, it will be very hard to crack. Or if you don't have the right information for your decoder, it will be hard to crack. For future work, I would like to implement this same type of techniques with echo and phase masking, and see, maybe do a comparative study to see which one is the best, faster, most efficient, uh, and determining a protocol for defending against attacks like white noise or interference, or people trying to see my hidden message that are not supposed to. And also, my ultimate goal was trying to video encode or encode a video into an actual audio file, which would be great if the video and the audio file can play as the signal is being uh, ran through or carried out. I have a demonstration on YouTube. You will go check it out. I'm sure you'll go check it out. It's the same stuff pertaining to steganography with frequency masking and hiding messages, and the same stuff that we just seen in results. And that is my presentation.